Greetings to everyone. It is my pleasure to participate in this NANO 2017 conference. In this occasion, I will present this talk which deals with new investigations related with lanthanide-doped magnesium oxide obtained by a glycine-based solution combustion synthesis. I will show the influence or the role of addition of lithium ions on this lanthanide-doped magnesium oxide, mainly on the thermoluminescence properties. As an introduction, I will explain the solution combustion synthesis, also known as the self-propagating high temperature synthesis. It is a redox reaction. In this process, there is a metallic nitrate and a fuel. They react. In this case, also the metallic nitrate is an oxidizer. The fuel is the reducing agent. You can add also the dopant salts in the form of chlorides or nitrates mainly. After the reaction, the solid combustion product is obtained. Historically, by this technique, many materials have been synthesized, such as refractory oxides, semiconductors, magnetic materials, isolators, and some others. So you can see in this picture a solution combustion process is carried out. At the same time that the flame is observed, the solution combustion product is formed. A very important parameter we need to take into account is Phe, which is the stoichiometric coefficient. Is the summation of all the oxidizing elements in the oxidizer and fuel divided by the summation of all the reducing elements in the oxidizer and fuel. You can have three possibilities: a fuel lean, fuel rich, and a stoichiometric environment. In the fuel environment, Phe is greater than 1. Fuel rich environment, Phe is smaller than 1, and in the case of stoichiometric, Phe is 1. In the case of fuel lean and fuel rich, we can say that there is a non-stoichiometric environment. In this case, you can add intrinsic impurities before thinking about doping. Now, talking about stimulated luminescence, we can observe this plot, which is the intensity of light as a function of time. At the top of this plot, we can observe the intensity of the exciting radiation, which is the excitation source. In the case of fluorescence, we can observe that as long as you have the excitation source, you will have emission. Once you remove this excitation source, you will not observe emission anymore. In the case of the phosphorescence intensity, you will have a persistent luminescence or afterglow, which is the luminescence you can observe after you remove the excitation source. The difference between fluorescence and phosphorescence is the time of this luminescence, but one of the main factors deciding whether it's fluorescence or phosphorescence is the temperature dependence on phosphorescence. In the case of thermoluminescence, this is a phenomenon you can observe after you observe this afterglow luminescence, and has to do with the temperature or the thermal excitation or stimulation after you irradiate the material, mainly with ionizing radiation, such as beta radiation, alpha radiation, or gamma rays, for example. So if we talk about thermoluminescence, according to band theory, we can observe three stages, which are irradiation, storage, and eviction, or recombination. In the case of irradiation, For example, if it goes with beta radiation, we can form, or we can observe this whole electron pair. The electron can go to the conduction band if the energy is sufficient, and then when the electron goes to the conduction band, it can be trapped, which is the storage stage, in these trapping states, which are metastable states or energy states. And then we can have the thermal stimulation when the electrons can be delivered from the trapping states and goes to the recombination centers, which are color centers. And this is the eviction stage. And we can also have, instead of thermal stimulation, we can have an optical stimulation, and you can have optically stimulated luminescence, for example. Now, regarding magnesium oxide, there have been several reports or publications on doped and co-doped magnesium oxide. For example, Boss et al. They reported OSL and TL of magnesium oxide doped with terbium. There have been also different works reporting different shapes of magnesium oxide nanoparticles. And in the case of Gu et al., he reported previously magnesium oxide, which is co-doped with lanthanides and lithium. And they reported also enhanced radioluminescence and photoluminescence signals, but this is not a thermoluminescence study, only for fluorescence. And in the case of Oliveira et al., they reported several reports, including this one of magnesium oxide doped with gadolinium and lithium. And this is a very suitable material for OSL and TL dosimetry. And previously, we reported this paper on luminescent properties of magnesium oxide, which was produced by solution combustion synthesis and doped with lanthanides and lithium. In this case, we reported stimulated luminescence in general, which is radioluminescence, thermoluminescence, and also some TL dosimetry features. And we made kind of a comparison between different lanthanides and the effect on these stimulated luminescence signals. And we observed that we could make this kind of toning of the thermoluminescence signal and the radioluminescence signal according to the dopant, and also to the molar ratio of the oxidizer and the fuel, which is the reducing agent, as I mentioned before. In the work mentioned before, all the phosphorus synthesized or produced by solution combustion synthesis were obtained by using urea as fuel. And in order to improve TL peaks positions and dose response linearity range, we proposed to change the fuel from urea to glycine and to make a glycine-based SES process. And why glycine? Because this organic molecule is a sweeter ion, which means it has a positive and a negative charge at the same time. And in the case of the negative charge, which is the carboxylic group, this group can, if I may say, trap divalent ions, which are metals in general. And in the case of the amino group, this group can trap trivalent ions, which are most of the times the lanthanides, at the same time. So it is very convenient to form this kind of chemical complexes named chelates, which are very stable complexes, and these ions can remain in solution instead of going on precipitation, because sometimes if they go as precipitates, they can form many compounds, let's say side compounds, which are not desirable and can diminish the yield of the combustion product that we want to obtain. It is important to add that glycine forms more stable chemical complexes than urea because of the higher value of the stabilization constant, which is the equilibrium constant on chemical complexes. In this respect, then using glycine as fuel, we obtain the following previous results. In the first place, we could obtain magnesium oxide doped with cerium and lithium, the same as the one obtained with urea. In this case, we obtained the crystalline phase mixture of magnesium oxide and cerium oxide. And according to the X-ray diffraction analysis, and in the case of scanning electron microscopy, we observe particles in the range of hundreds of nanometers with non-defined forms or shapes. In the case of thermoluminescence results, we can observe in the graph on the left the TL growth curves from pure magnesium oxide, magnesium oxide cerium doped, and magnesium oxide cerium and lithium co-doped. So there's a significant difference between the co-doped sample and the lanthanide-doped and pure magnesium oxide growth curves because of different peaks located at very stable temperatures, talking about TL dosimetry. So this is caused by this compensation charge effect between the lanthanide, which is cerium, and lithium. And if we can observe the graph on the right, this is the dose response curve, which has a linear trend within the interval studied of the dose. And it is important to add that comparing with the results obtained previously with the urea-based solution combustion synthesis for the same material, we can observe a, let's say, an additional component located at around 400 degrees Celsius. And also we can observe that the linearity was enhanced at around 2 times comparing to the urea-based sample. And this is an important result because the interval studied is increased, talking about the TL dosimetry. So it is worth mentioning that in the case of the dose response curve, or at any curve that has indicated integrated TL, integrated TL is the area beneath a glove curve depending on the measurement. For example, if it's the evolution of the glove curve as the dose is increased, we can have this area beneath each glove curve at different doses. In the case of the TL fading, we can obtain this integrated TL from the area beneath each glove curve at different storing or storage times. Also, we can observe a very good signal repetibility, and as we can observe on the TL decay curve, we can see this asymptotic behavior during 1 month, which is very suitable for practical dosimetry. Because if you have your sample and you want to analyze this one on a TL reader, if you can have a very stable signal which doesn't fade on time, it is very convenient, because you will have electron stored for a very long time. In the case you want to analyze how much radiation your sample absorbed in some process. All these results we could publish on this paper on thermoluminescence of novel magnesium oxide, cerium oxide obtained by a glycine-based solution combustion method. So we continue to work with different lanthanides than cerium, and to see the effect on the thermoluminescence properties and also structural properties. We continue to use the same methodology regarding solution combustion synthesis. So previously to the combustion, we evaporate at 200 degrees Celsius the mixture or the initial solution of the metallic nitrate, which is the magnesium nitrate, and the glycine, and of course the lanthanide salts in the form of nitrates, and in the case of lithium, using lithium chloride. So we stir this mixture during 30 minutes, and then we increase the temperature to 200 degrees. After the evaporation process, we increase the temperature up to 500 degrees, and after around 7 or 10 minutes we can observe the solution combustion product, which is a powder. And previously to this formation of this solid, we can observe the mentioned flame and this fumes emission. All of this process we carried out on the fume hood in the terms of security. And for measuring TL, we use the commercial equipment RISO TL OSL reader model DA20. This equipment is built with a beta radiation source of strontium 90, and in the case of X-ray diffraction and scanning electron microscopy, we use the equipment from our department. We use this equipment in general for characterizing the most recent materials synthesized by SCS. In this respect, our most recent materials obtained are magnesium oxide doped with europium, lanthanum, and dysprosium, and co-doped with lithium, the 3 types of materials. One of our new materials obtained is magnesium oxide, europium, and lithium doped. This material is obtained by a glycine-based solution combustion synthesis. So we can observe a TL glove curve with a very intense maximum or peak located at around 360 degrees Celsius. So we can observe that this interval where the peak is located is a black body radiation interval or incandescence But we observe that as the dose is increased, the intensity of light is also increased. So this is the way that we can identify TL. And also we couldn't observe any saturation evidence on the interval studied, and this is kind of a broad peak. And we can observe that as the dose is increased, the position of the peak remains, which is characteristic of a first order kinetics for the TL processes. We could obtain a linear trend on the dose response curve, which is a very good calibration curve of the material. It is desirable to have a linear trend, and we couldn't see, supported with the previous figure, any saturation evidence. And for this material we can consider that the useful range is for low doses, namely personal dosimetry or environmental dosimetry, for example. And in the case of TL fading, we can observe for this decay curve on the right that this material showed an asymptotic behavior, which means that the signal is stable. Regarding the time of storage, which is also a very desirable feature for TL dosimetry. Another novel material that we could obtain is magnesium oxide, but now lanthanum and lithium doped. In this case, for the XRD analysis, we can observe the mixture of two crystalline structures or phases corresponding to magnesium oxide and lanthanum hydroxide. So in the case of the SEM image, we can observe particles with different shapes and sizes between 5 microns and 100 of nanometers, and with no porosity observed. And in some cases we can observe also this sintering effect on some particles. In this graph we can observe the difference between TL glove curves of pure magnesium oxide, lanthanum doped, and magnesium oxide lanthanum lithium doped. So for the co-doped sample with the lanthanide and lithium, we can observe a significant difference between the other two TL glove curves, because in this case there is the appearance of two different components at very stable temperatures, and we have this low temperature peak, which can be useful for another applications as persistent luminescence application or afterglow. In this case, analogous to the cerium lithium doped sample, we could observe the compensation charge effect of lithium on the lanthanide sites in the crystal structure of magnesium oxide. There is a glove curve evolution for different doses for this material in the interval from 1 gray up to 16 grays. So we can observe that there is no evidence of saturation in the studied interval. And another important thing to add is that usually magnesium oxide, also doped and co-doped in previous works, was proposed for low doses But in this case, according to the interval studied and to the behavior of this globe curve, we can propose this material as suitable for medium dose dosimetry application, which is the first time that someone proposed this kind of material based on magnesium oxide for this interval. Moreover, we can observe very desirable features for TL dosimetry on this material, such as a linear trend of the dose response in the range of doses studied, and also an asymptotic behavior of the TL decay curve, which means we have a very stable signal during the time of storage of electrons. And with these two features, we can propose this material as suitable for the dosimetry applications I mentioned before. So, as I mentioned before, regarding the peak located at around 90 degrees Celsius, this peak it's an indication that this material could be suitable for afterglow or persistent luminescence applications. So in this case, we measure the afterglow intensity as the dose was increased. So we can observe that the afterglow intensity increases, and the inset graph is the linear trend from the integrated afterglow, which is the area beneath each decay curve for different doses for this afterglow property. So with these two results, we can conclude also that this material is suitable for persistent luminescence applications, or we can say real-time dosimetry, or let's say retrospective dosimetry applications. And another remarkable result for magnesium oxide based materials is the one we obtain, dysprosium and lithium doped. So we can observe from the TL globe curves that there is a very useful interval for medium doses between 0.5 grays up to 16 grays. So we can observe at least two maxima located at very stable temperatures, and as we increase the dose, the intensity was increased on the globe curve. Also, we can observe that as the dose increases, so the intensity increases, but the peaks remain on the same positions, which is an indication of first order kinetics for the TL processes, as we could observe for another materials shown in this presentation before. So we could observe, as with the previous materials, very desirable features for this one, talking about the dose response and the TL decay curve, because the dose response was linear in the interval studied, and for the TL decay curve we could observe this asymptotic behavior as a function of time or storage time. So we could observe that also if you change the lanthanide in general, you can have different signals or different TL globe curves with very desirable dosimetry features. Thereby, we can obtain also host materials based on lanthanides. This is the case of lanthanum oxide. We can see that this TL globe curve is very suitable for dosimetry applications. So not only for the dopants but also for host materials, we can obtain by this technique very suitable phosphors for TL dosimetry applications. In this case, we can say that this material is useful for high dosimetry applications. And we can observe the sintering process for the particles on the SEM image at the right, so which is a very desirable property for the morphology in terms of size particle for toning or modifying the TL signal. And finally, as our main conclusions, we can say that SES was an appropriate method to synthesize magnesium oxide with lanthanides and lithium as promising materials for radiation dosimetry applications. We can say that TL properties could be enhanced by changing the fuel from urea to glycine in terms of peak positions, in terms of linearity range on the dose response curve, and also an improvement of on the TL fading in terms of storage times, which was increased significantly. Another conclusion we can have is that lithium, or the lithium ion, increases the intensity and shape of thermoluminescence in the case of lanthanide-doped magnesium oxide produced by SES, possibly due to charge compensation effects with lanthanides as dopants. This effect we observed before in the case of the cerium and lithium magnesium oxide doped. And the TL globe curve toning was observed as the type of lanthanide dopant was changed within the host lattice of magnesium oxide. But further structural characterization is necessary to determine crystalline phase for different magnesium oxide, lanthanide, lithium powders, and also to see not only the role of lithium but also maybe by X-ray photoelectron spectroscopy to see the chemical environment of lithium for detect this ion and to see exactly not the effect but the specific position lithium has within the crystal structure of magnesium oxide. As acknowledgements, we will thank to the funding agencies in Mexico for giving us resources for carrying out this research. Also my colleagues, Professor Catalina Cruz Vasquez and Professor Rodolfo Bernal. We collaborate in the same research group, and also it's very interesting because we could compare different techniques that these two professors use with solution combustion synthesis for similar materials. And mainly to my associate students, because they do synthesis and characterization of these materials constantly. In the first place, to Flor Escobar Ochoa. She synthesizes magnesium oxide doped with different lanthanides and lithium. In the case of Maria Gortares Jimenez, for synthesizing specifically magnesium oxide europium lithium doped. In the case of Gustavo Sanchez Ortega, for synthesizing magnesium oxide dysprosium lithium doped. And Adriana Lara Gonzalez, she is exploring the possibility, like I mentioned before, for synthesizing a host material based on lanthanide, in this case lanthanum oxide, but using an urea-based SES. And finally, and more important, I really appreciate your attention to this presentation. I would like to receive further comments on this line of research we carry out during the past 5 years, and I hope we can collaborate in the future if you're interested. And again, thank you very much.